So let's start with L1 and L2 regularization. So this is a way to keep the weights low in our neural network. And of course, now you might ask, but what does weight have anything to do with overfitting? Well, let's remember what a weight is, right? So a weight is basically something, the importance of the connections here, right? This connection will have a weight, this connection will have a weight, this connection will have a weight. And the weight will determine how much importance we put to the output of this neuron that goes into this neuron. So you can think of it as the importance of an input, the importance of the input that goes into this neuron here. So, you know, let's take this specific one here. And how does the graph look like when we are overfitting? Right, so we have the input, we have the output, and when we are overfitting, our model will look something like this. Well, what does that mean when you think about it? It actually means that this specific input feature, because this is just one feature, right? We might have multiple features. It means, the fact that it is overfitting means that this input has a lot of importance. Your model thinks whatever this input says is true. So what would that mean? If we're trusting this input so much, it will mean that its weight is very high. So the input in this case could be the one that's coming from here, the one that's coming from here to the output. That means that your model thinks the importance of this specific one is very high. And that's basically what happens. When your model overfits, you have very high weights. And that's why with L1 and L2 regularization, we are trying to find a way to keep your weights low so that your model will not overfit. So let's see how we do that. The general idea, the intuition, is that, you know, we have the loss function, right? That's how we update our model. We make predictions, and then we have the actual values. And based on the loss function, we are able to calculate the error. Based on that error, the model is updated. How L1 and L2 regularization work is they add to this loss function the weights. And they do it in two different ways, but basically we are trying to penalize the model, the network, for the higher weights that it has. So the higher the weights, the more penalized it would be. So in the end, it will be in the model's favor, let's say, to keep the weights low so that it will not be penalized. So let's look at the L1 regularization specifically. It is also called L1 norm or Lasso in different places. So if you see it, this is basically what people are talking about. And that one has basically the power of making the network sparse. And what I mean by sparse is, so we have a normal network, right? And every little neuron is connected to every other neuron. But if I take one neuron out, some of the connections are not going to matter anymore because there is no neuron here. It's not going to fire. It's not going to give me an output. And that will make your network sparse because you're going to, not all the neurons are going to be connected to each other. L1 regularization, as I said, adds the weights to the loss function to penalize the network to having higher weights. And how it does is basically it adds the absolute values of the weights to the loss. So weights might have, we're saying absolute values here because weights might have negative or positive values. So if you just sum them up, they might just be zero. So if you have weights that are like -4, -3, -1, and you also have weights that are 4, 3, 1, if you sum all of them, you're going to have 0, and then your model is not going to be penalized. Whereas what you want to do is get the absolute value, so even if they're negative, you're going to turn them into positive, sum them up, and then add that to the loss function. And doing that, L1 regularization effectively encourages the neurons or the weights to be 0, and that way it eliminates some of the weights. So basically those weights are not going to be connecting the neurons anymore. Effectively, we're going to miss some of the neurons in between, and our network is going to be sparse. L2 regularization works a little bit more differently. Sometimes they call it a bit more nuanced. Again, it's called ridge regression, more in the statistics part of things, or it's sometimes called weight decay. So just so you know, if you see these terms, you know what they're talking about. This one works with squared values, so it sums up the squared values of the weights. So what happens is, if you get a square of a number that's higher, you're going to get a much higher value than if you're getting the square of a value that is lower. So, you know, you can see the square of 2 is 4, whereas square of 12 is 144. So there's a much bigger difference between the square of those two numbers. So what happens is, then you are penalizing the network for higher weights at the end of the day, and that's why it doesn't end up in sparse weights as much as the L1 one, but L1 regularization. But at the end, you get a network where some of the weights are penalized a little bit more, some of them are penalized a little bit less. So the effect is a little bit different all over the network. Of course, you can decide how much to affect your network with these penalties. After you decide which one to use, or maybe both, to use both, you can decide how much the network needs to be penalized. So you do that with the alpha parameter. So you can think of this as, you know, regularization, whether to do regularization or not is one hyperparameter for your network. Which regularization technique to use, or which ones to use together, is another hyperparameter. That's something that you need to decide. And on top of that, if you choose to use L1 or L2 regularization, you also need to decide the alpha parameter, and that is the thing that you'll tell the network how much to penalize using the weights. If you do the penalty, if you make the penalty too strong, then your model, you will have a chance or the risk of underestimating the weights, making them very, very small, and then you will not be able to actually fit the model. So your model is going to be very simple, right? So the regularization is, what it does is simplify the model. So if you penalize your model too much, the weights are going to be lower. That means your network is going to be very simple, and that simple network is not going to be able to fit your data very well. Whereas if you do the penalty too weak, then regularization is not going to help you so much, and at the end you might overfit after all. When we're doing the practical exercises, we will talk about how to set these values, but just so you know, if you set it to 0, it means no penalty. If you set it to 1, it's full penalty, so it's a range between 0 and 1. Let's talk about some tips on how to use these two. So basically, you can use them with all network types. You can use them with RNNs, CNNs, deep neural networks, whatever you want, they'll work for you. You might need to change them a little bit specific to the network that you're using. Of course, you might need to use, while you're coding, you might need to use different libraries or call different functions, but at the end, these two regularization techniques will work for all types of neural networks. Of course, then you need to normalize your inputs for the best results. What is normalizing? Let's recap that. That is making sure all your inputs are in the same range. Last one is that's good to know is that you can actually use both of them together. You don't have to choose one or the other. And I think there are some research that is done here, and it shows that using them together actually gives you a better result than using them separately. But of course, this might depend on your problem.